Maximum a posteriori hypothesis, brute force Bayes concept learning. First we will discuss what is Bayes theorem. Bayes theorem is the cornerstone of Bayesian learning because it provides a way to calculate the posterior probability, that is probability of H given D, from the prior probability, that is probability of H, the probability over the data, that is P of D, and the current probability of D given H. The Bayes theorem looks something like this. Probability of H given D is always equivalent to probability of D given H, probability of H divided by probability of D here. Now what is maximum a posteriori hypothesis? The learner considers some set of candidate hypothesis H and is interested in finding the most probable hypothesis H belongs to H given the observed data D here, or at least one of the maximal probable if there are several probable hypotheses. Any such maximum probable hypothesis is called as maximum a posteriori hypothesis, that is MAP hypothesis. We can determine the MAP hypothesis by using Bayes theorem to calculate the posterior probability of each candidate hypothesis. More precisely, we will say that HMAP is a maximum a posteriori hypothesis provided HMAP is always equivalent to argmax over H belongs to H probability of H given D. That is, we need to find out the posterior probability of all the hypotheses and we need to select one hypothesis which is having the maximum value. So if we replace the probability of H given D with the Bayes theorem, probability of H given D is always equivalent to probability of D given H, probability of H divided by probability of D. This probability of D is common for all the hypotheses, so we will ignore it. Hence, the HMAP is always equivalent to argmax of H belongs to H, probability of D given H, probability of H here. Now we will discuss what is brute force map learning algorithm. There are two steps in brute force map learning algorithm. The first step, for each hypothesis H in H, calculate the posterior probability. So first we will calculate the posterior probability for every hypothesis in the hypothesis space. Next what we do is we will calculate the maximum among those and we will output it as a HMAP. So that is the second step here. This algorithm may require significant computation because it applies Bayes theorem to each of the hypotheses in hypothesis space to calculate the posterior probability. While this is impractical for large hypothesis spaces, the algorithm is still interesting because it provides a standard against which we may judge the performance of other concept learning algorithms. It is impractical because when we have a large hypothesis space, we need to calculate the posterior probability of every hypothesis, but it provides a judgment we can judge the performance of other concept learning algorithm with the help of Bayes theorem. Now, how to solve that particular difficulty? That is, while calculating the posterior probability, we need to consider the prior probability as well as the current probability. Is there any way to reduce that particular computation? So what we can do here is we can assume some conditions like the training data is noise free, the target concept C is contained in the hypothesis space H, and we have no prior reason to believe that any hypothesis is more probable than any other. Given these conditions, we can calculate the posterior probability with the minimum computation. Given these assumptions, first we need to calculate what is the value of probability of H, that is the prior probability. As given in the assumptions, there is no prior knowledge that one hypothesis is more likely than other. Hence, every hypothesis has the equal occurrences. Hence, the probability of H, that is the prior probability, is always equivalent to 1 divided by cardinality of H, where cardinality of H is the Gaussian space. Similarly, what will be the choice for probability of D given H, that is the current probability given those three assumptions? Probability of D given H is the probability of observing the target values, that is D is equivalent to D1 to Dm for the fixed set of instances x1 to xm. Now, if the hypothesis is consistent with the training examples, the probability of D given H is 1, otherwise it is equivalent to 0 in this case. Hence, we can put that particular thing something like this: probability of D given H is equivalent to 1 if the hypothesis is consistent, otherwise it is 0 here. The consistency is the di is the target and h of xi is the output of hypothesis H. If both of them are same, it is consistent. If the hypothesis is consistent with the training example, it is 1, otherwise it is 0. That is the probability of D given H here. Now, we will try to put these particular values into the Bayes theorem, and we will try to calculate the posterior probability. So, to calculate the posterior probability, first we will assume that the hypothesis is inconsistent, that is the H is inconsistent with the training examples. If H is inconsistent, the probability of H is equivalent to probability of D given H is equivalent to 0. So, if you put that particular value, the posterior probability will become 0 if H is inconsistent with the training examples. Now, the other possibilities, the H may be consistent with the training examples. So, we will consider that here. If H is consistent with the training examples D, probability of D given H is 1 whenever H is consistent. So, we will put those particular values. This is the Bayes theorem. Probability of D given H is 1. Probability of H is equivalent to 1 divided by cardinality of H here. Now, what is the probability of D? Probability of D is like the probability of a data set when the hypothesis is consistent. So, we can say that this is equivalent to the number of consistent hypotheses over all the hypotheses. So, the set of hypotheses is always given by the Gaussian space. So, the probability of D is always equivalent to the cardinality of Gaussian space divided by cardinality of hypothesis space. Now, this H and H will get cancelled. Probability of H given D, that is the posterior probability, is equivalent to 1 divided by cardinality of Gaussian space here. So, Gaussian space is nothing but set of all consistent hypotheses. So, the posterior probability when H is consistent with the training example is equivalent to 1 divided by cardinality of Gaussian space. Finally, given those three conditions, we can calculate the posterior probability using Bayes theorem with these equations. Probability of H given D, that is the posterior probability, is always equivalent to 1 divided by cardinality of Gaussian space if H is consistent with D, 0 whenever H is inconsistent with D. Hypothesis and least squared error hypothesis. Many learning approaches such as neural network, linear regression, and polynomial curve fitting try to learn a continuous valued target functions. If you want to use the continuous valued target functions with respect to Bayesian learning, is not possible directly. Under certain assumptions, any learning algorithm that minimizes the squared error between the output hypothesis predictions and the training data will output a maximum likelihood hypothesis. The significance of this result is that it provides a Bayesian justification for many neural network and other curve fitting methods that attempts to minimize the sum of squared errors over the training data. In order to find the maximum likelihood hypothesis in Bayesian learning for continuous valued target function, we start with maximum likelihood hypothesis definition, but using the lowercase p to refer to the probability density function. That is, HML is equivalent to ARG max, probability of D given H for all H belongs to H. Here we have considered P as a small case to indicate it is a probability density function. We don't know the actual probability of D given H in this case because the target is distributed continuously. We assume a fixed set of training instances x1, x2 till xm and therefore consider the data D to be the corresponding sequence of target values d1, d2 till dm. Here the target value is continuously distributed. Now we can write probability of d given h as the product of the various probabilities of di given h because d is constituent of d1 to dm in this case. That is, HML is equivalent to ARG max, product of I is equivalent to 1 to m, probability of di given h over all the hypotheses from hypothesis space. Here, now we assume that the target variable or the target values are normally distributed. If the values are normally distributed, we can use the probability density function of normal distribution. The probability density function of a normal distribution is always equivalent to 1 divided by square root of 2 pi delta square multiplied by e raised to minus x minus mu bracket square divided by 2 times delta square, where delta is the standard deviation, x is the input, mu is the mean. In this case, I have assumed that delta is constant, hence I have not considered delta in this equation. Probability that's f of x given mu is equivalent to this equation. Now what we do here is probability of di given h, that is we assume that the probability is distributed with the normal distribution, hence we can replace this particular thing with this equation. Here x will become di and mu will become, that is, h of xi because it is for ith input. So this will look something like this. HML is equivalent to ARG max, product of 1 divided by square root of 2 pi delta square e raised to 1 minus 2 times delta square multiplied by di minus mu bracket square. In the first step we have replaced x with di. In the second step what I did is I have replaced mu with h of xi. This is the di is the target of ith input and h of xi is the output of hypothesis for ith input in this case. Now we'll apply a transformation that is common in maximum likelihood calculations. Rather than maximizing the above complicated expressions, we shall choose to maximize the less complicated logarithm because the logarithm function is a monotonic function. That is, ln of p increases as the value of p increases, ln of p decreases as the value of p decreases. Hence, we can use ln to reduce the complexity of this expression. If you put ln on the right hand side, it will become something like this. The product term will be changed to summation term here, and in this case we have ln of this entire term. This entire term is a combination of two things, that is 1 divided by square root of 2 pi square into e raised to this term. So we consider that this is x and this is y. Ln of xy is equivalent to ln of x plus ln of this one. Again in the second case, ln of e raised to minus 1 divided by delta square 2 times delta square di minus h of xi bracket square. So this can be written like ln of e raised to x is equivalent to x of ln of e. So this will become minus 1 divided by 2 times delta square di minus h of xi bracket square ln of e, and ln of e is equivalent to 1. So finally we are getting something like this. So product term is changed to summation term. Ln of 1 divided by square root of 2 times pi delta square minus 1 divided by 2 delta square di minus h of xi bracket square, and ln of e is the term here and it has been changed to 1 here. Now we will try to remove the constant term because we are interested in the hypothesis which is having the maximum value. If I use the constant in this equation, the same constant will be added to all the hypotheses. So we try to remove those particular constants rather than considering in every hypothesis. So this is the first constant we are going to remove. If I remove this constant, the equation becomes something like this. Now if you look at this equation, we have minus here. So I will take this particular minus outside. If I take minus outside, this ARG max will become ARG min. That will look something like this. Again in this equation we have 1 divided by 2 times delta square, that is the constant term. As I have already told, I have considered standard deviation as a constant term. So I will remove this 1 divided by 2 delta square. So if I remove this particular thing, the final equation looks something like this. HML, that is the maximum likelihood hypothesis, is equivalent to ARG min summation of I is equivalent to 1 to m di minus h of xi bracket square for all the hypotheses. Now what this particular equation indicates is the maximum likelihood hypothesis is one which is having the minimum error between minimum squared error between the hypothesis, minimum or the least squared error between the hypothesis. So what this equation indicates is the maximum likelihood hypothesis is always equivalent to the hypothesis which is having the least squared error hypothesis. So in this case, di is the target and h of xi is the output of an hypothesis h, and di minus h of xi is the error, and it is a squared error. So that is the reason HML is always equivalent to least squared error hypothesis. So this is the maximum likelihood hypothesis for Bayesian learning given continuous valued target attributes. I hope you understood what is maximum likelihood hypothesis for Bayesian learning given continuous value target output. What is least squared error hypothesis? Bayes classifier to classify the example into one of the given categories. In this case, we have been given a data set with 14 examples. There are 4 attributes in this case, namely outlook, temperature, humidity and wind. Play tennis is a target variable with 2 possible outcomes. One is no and another one is yes. In this case, we have been given a new instance with certain conditions. We need to check whether the new instance can be classified as either yes or no. Now if you want to classify the new instance into either yes or no or one of the categories, very first thing what we need to do is to calculate the prior probabilities and then the current probabilities. So the prior probability is in this case is the probability of yes and the probability of no. So if you count the number of times yes is appearing 1, 2, 3, 4, 5, 6, 7, 8 and 9 number of time, and the remaining 5 times no is appearing. So the probability of yes is 9 by 14 and the probability of no is 5 by 14. So this is the prior probability. Probability of play tennis is equivalent to yes, which is equivalent to 9 by 14. Probability that play tennis is equivalent to no, which is equivalent to 5 by 14. Once you calculate the prior probabilities, next we need to calculate the current probabilities, that is also called as conditional probabilities of individual attributes. Here we have 4 attributes: outlook, temperature, humidity and wind. We need to calculate the conditional probabilities of all these attributes. Here I have written the attribute name and the possible outcomes of this attribute is written here, and these are the possible values of this attribute. Now we know that there were 5 yes examples are there. We know that there are 9 yes examples are there and 5 no examples are there. Out of this 9 and 5, yes and no examples, we need to count how many number of times Sunny is appearing in yes and no respectively. Similarly, how many times overcast is appearing in yes and no respectively, and rain is appearing in yes and no respectively, so that we can calculate the conditional probability. Now, if we count Sunny is in the first case, Sunny is appearing in no example. Second one is no. Third one is no. Fourth one is yes, and fifth one is yes here. So there are two yes examples are there, and three no examples are there. That is 2 by 9 is the probability that outlook is equivalent to Sunny given yes, and 3 by 5 is the probability that outlook is equivalent to Sunny given no. Similarly, we need to calculate it for overcast. Overcast is appearing in yes, second one is in yes, third overcast is appearing in yes, and fourth one is also in yes. So the probability that outlook is equivalent to overcast given yes is equivalent to 4 by 9. Probability that outlook is equivalent to overcast given no is equivalent to 0 by 5, that is equivalent to 0. Similarly, we need to calculate the conditional probabilities of all the attributes and the possible values of those particular attributes. So this table shows how can we calculate the conditional probabilities. You can pause the video for a minute and try to calculate the conditional probabilities. If you find any difficulty, we can put those difficulties in the comment box so that we can address those things at the later part. Now once you calculate the prior probability and the conditional probabilities, the next task is to classify the new instance into either yes or no class here. So the new instance is outlook is equivalent to Sunny, temperature is equivalent to cool, humidity is equivalent to high, and wind is equivalent to strong. So these are the conditions given to us. So given these conditions, whether this new instance belongs to yes or no, we need to find it out. So this is the nearby classifier equation. VNB is always equivalent to argmax of Vj belongs to yes no. Here S and no are the two target values we have. Probability of Vj multiplied by product of probability of AI given Vj, where AI is the set of
madam.
attributes and Vj is the possible outcome in this case. So first we will replace
Mechanical.
AI with given conditions. The
ಯಾರಿಲ್ಲ
AI
ಇಲ್ಲ
is given
ಇವತ್ತು
like outlook is equal
ಡಿಪಾರ್ಟ್ಮೆಂಟಲ್ಲಿ
to
ಸುಮಾರು
sunny,
ಜನ
temperature is equal to cool, humidity is equal to high, and wind is equal to strong.
ಹಾ
The
ಈ
same thing I have
ಕಡೆಯಿಂದನೇ
written it
ಹೋದ್ರೆ
over here.
ಸಿವಿಲ್ ಆ ಕಡೆ
Next,
ಮೆಕ್ಯಾನಿಕಲ್
what
ಈ
we need
ಕಡೆ
to do is we need to replace
ಡ್ರಾಯಿಂಗ್
yes
ಅಲ್ಲ
by
ಒಂದು ಡ್ರಾಯಿಂಗ್ ಅಲ್ಲ
yes
ಮ್ಯಾಥ್ಸ್
first time
ಡಿಪಾರ್ಟ್ಮೆಂಟ್
and
ಪಕ್ಕದ್ದು
no
ಹಳೆ
second time,
ಮ್ಯಾಥ್ಸ್ ಡಿಪಾರ್ಟ್ಮೆಂಟ್
and then we need to calculate the probability. Depending on that
ಇವತ್ತು
probability, we
ಯಾರು
can
ಬಂದು
decide whether the particular person will play the
ಹಾ
tennis or will not play the
ಹಾ
tennis given these
ಅಲ್ಲೇನು
conditions. So phi and b of yes is always
ಅದೇ
equivalent to
ಹೋಗೋಣ
probability of yes, that is Vj is replaced by yes here, and this Vj should be replaced by yes, and so on. So probability of sunny given Vj, that is yes, probability of cool given yes, probability of high given yes, probability of strong given yes. So we need to put the values what we have calculated in the previous slide. That is probability of yes is equivalent to 9 by 14, and the probability of sunny given yes, that is probability of sunny given yes, is equivalent to 2 by 9. Similarly, we need to put all the values here. We will get the answer as 0.0053. With the same note, VNB of no we need to calculate. That is Vj is equivalent to no in this case. Probability of no, probability of sunny given no, probability of cool given no, probability of high given no, probability of strong given no. If you put all the values in this equation, we will get 0.0206 as the probability. If you compare these two probabilities, the probability of no is more than the probability of yes. It means that the new instance is classified as no. The meaning is the person is not going to play the tennis. There is one more thing we need to do, that is we need to normalize these probabilities, because these are the equivalent probabilities, because we have removed the denominator term. So if you want to consider that, we need to normalize it. The normalized values can be calculated something like this. Phi n b of s is always equivalent to Phi n b of s divided by Phi n b of s plus Phi n b of no. If you put the values here, you will get 0.205 as the probability, and Phi n b of no is always equivalent to Phi n b of no divided by VNB of yes plus VNB of no. So again, if you put the values, you will get the probability as 0.795. If you add these two probabilities, that's the probability of yes and probability of no, it is equivalent to 1 in this case. So this is the one measurement, the thing you can consider while cross-checking whether your answer is correct or not. Now if you compare these two probabilities, the probability of no is more than the probability of yes, hence the new instance is classified as no here, meaning the person will not play the tennis. So in this video we understood how to calculate the prior probabilities, how to calculate the conditional probabilities, and how to use those prior probability and conditional probabilities to classify the new instance.
Hello.